right. We should be able to go a half an hour.
All right.
Should we start here?
Yeah, we only have to do a couple of these to make sure I got it, because this is going to be on our test tomorrow, maybe?
Okay. Tell me which ones.
So, like, 18, 19, and, like, 21.
All right. Once you know how to do one of these, you know how to do all of them. Whenever you have exponential equations, which is what this is because the variable is in the exponent, you're going to usually have to use logs to solve it. If we're going to use logs to solve it, our first goal is to isolate that.
All right.
So, get me started here.
So add 23 to both sides.
You mean,
Or add, no, add 17 to both sides. So 5e 12x equals 40. Then divide it by 5. Both sides by 5. Alright. Then would you take the log of, or not the log, the other one, in, or whatever?
the natural log?
Yeah, the natural log.
Yeah, they're both logs. In other words, log was correct. You could have taken any kind of log you wanted, but the natural log's the one that's the most efficient. In other words, if I take the natural log, ln, not in, ln, of both sides, now what does that allow me to do with the 12x?
Bring it in front of the
Yeah,
in.
I can basically
Or
write it like this, but what is the natural log of e?
Is it just 1?
So I can replace that with a 1, which means the left side reduces to 12x. What's the last step?
Dividing both sides by 12?
There's your answer.
Okay, that makes sense.
That's all there is to any of these problems. They're all going to be basically the same. So let's make sure you can do 19 all on your own.
All right.
Give me a step by step.
All right, so subtract 1 from both sides, then divide it by 2. So
Give me line by line. What's the next line going to be? If you want to do 2 steps in one, that's fine with me.
all right, so e to the x, or yeah, equals 2.
Okay.
And then take the natural log of both sides, which is
So what's
x.
So the next line is going to be x equals
Natural log of 2.
okay.
Or, yeah.
Okay. And that's all you need to do here, as long as you understand what's going on. In other words, I'm actually taking the natural log of both sides for the third step, and it leaves x on the left.
All right.
All right, let's see. From what I see, 20 is easier. 21 is no different.
Except it's just a negative x.
Let's do 21.
That's
Is this a plus 8?
yeah.
Give me line by line.
Be e to the negative x, or actually
You don't need to
do
You
12.
don't need to do 2 steps at once. If there's
Yeah.
any hesitancy at all, do it in one step. Equals what?
Negative 1.
Next line.
Then divide both sides by negative 12.
Give me the next line. Yeah.
So e to negative x equals 1/12.
Okay.
And then take the natural log of both sides, which is negative x equals the natural log of 1/12. And then divide both sides by -1. So x equals natural log of -1/12.
No, you want to put the negative sign in front.
Oh, okay.
Okay. And that happens to be the same as, right? Because I can always take that exponent and put it down in front, which means I can always put whatever's down in front and make it an exponent. Okay, you with me?
Mm-hmm.
Which means
Yeah.
1/12 to the -1 is the same as,
12.
so that's what x is equal to, is natural log of 12.
Okay.
Okay? So when you get to this step right here, is all you're doing is dividing both sides by -1, which puts a negative in front of this function, not inside of it. It's like, well, it's like if I divide e to the x by -1, it doesn't make it e to the minus x. It makes it minus e to the x. Okay? All right, what else do you want to look at here? How about 22? Let's do 22. It's a little different. There's no e to the x.
Would you take the log of 2 both sides?
I would take the natural log of both sides.
Okay.
You could take the log base 2 of both sides. And we'll do it both ways, and I'll show you why I prefer the natural log. Okay? Take the natural log of both sides. Now, what does that allow you to do?
Make it 1.
No. The x comes down in front, but the natural log of 2 is not 1. In other words, is all for the moment that it allows me to do is this. You with me?
Yeah.
So x becomes natural log of 12 divided by natural log of 2. So there's your answer. 2 steps. Okay? Now let's do it the way you wanted to do it. Let's take the log base 2 of both sides. Okay? When we take the log base 2 of the left, what do we have?
Would it be just x?
Equals log, and we have to take log base 2. So it looks like that's the better method to use, right? Looks like only 1 step instead of 2 steps. But how do you get this number, log base 2 of 12? You don't get it out of your calculator. Your calculator only has common log, base 10, or natural log, ln. So in order to convert this, you've got to take the log of the big number 12, and I don't mean the highest, I mean the large number, over the log of 2.
I actually can plug the first one into my calculator because I have a
You have the
Inspire.
Oh, okay. Well, then maybe that's the better way to do it. But you will eventually maybe get to a position where you're more comfortable just always taking natural log. Natural log is such a key function. You don't ever see log base 2. And I mean never. Not in calculus, not in calculus 2, not in calculus 3. But you'll see natural log 100 times. Now, what's interesting about this problem is that this ratio right here is the same as this ratio, even though this is common log and this is natural log. Their ratios are always the same. In fact, log base 2 would be the same. I could put log base 2 in there, and those are the same things. Okay? So,
Yeah.
it doesn't really matter which technique you use. I'm not going to insist on one over the other. If you want to take log base 2 of that, that's perfectly fine, especially since you have the inspire. If you didn't have the inspire, then it wouldn't really be any faster. Which one do we want to do next? You said you only have to do some of them.
Yeah. 35 we can do.
Okay. Now, this happens to be one of the few that you can do without using logs. I don't know if they put this on here intentionally because of that, or whether they want you to use logs. But this is actually a classic problem that you're going to find on the SAT, and the SAT does not test on logs. But they will give you this kind of a problem. So let's do it two different ways. One way is to come up with a common exponential base for both of these numbers. What's the common exponential base for 9 and 27?
3.
Yeah, it's not 9, it's 3. And by that I mean I can write 9 as 3 squared, and I can write 27 as 3 cubed. Now I can apply the rules of exponents, which means the left becomes what? What's 3 squared to the x power?
Is it 3x, right?
We're doing double exponentiation, which means we have to multiply those exponents.
So 3 to 2x.
Equals what?
3 to 3x minus 6.
Okay. Now we have common base, different exponents. We can equate the exponents. So 2x equals 3x minus 6. Take the 2x to the right, the 6 to the left, you get x equals 6. Okay?
Okay.
Okay, so that's the way to solve that problem without logs. We don't need logs only because we can state both of these numbers in a common exponential base. Could we use logs to solve it? Certainly. What would you do?
Would you take the natural log of both sides?
I would, yeah. I like I said, I've become quite partial to using natural log. Now what's the next line?
So it'd be x natural log 9 equals x minus 2 natural log 27.
In parentheses. Okay. Now what do we do?
Would you move?
Remember that natural log of 9 is just a number, and so is natural log of 27. So if I were to substitute numbers for here, what would be your next step in the algebra of this?
Divide both sides by one number
Actually, it would be
for both
to
sides?
distribute the right side. Okay, let me give you this problem right here. 2x equals 3 times x minus 2. What would your next step be?
It would be 3x minus 6.
Right, and then you would solve that, right?
Yeah.
Okay, well, this is no different. That natural log of 9 is just like my 2. Put it in front of the x if you like. And so I have to distribute that. So I got natural log of 9, we'll leave the x in front, equals x times natural log of 27 minus 2 natural log of 27. Okay?
Yeah.
Now what's the next step from an algebra point of view?
Subtract or add 2 natural log 27 to both sides. And then subtract.
Okay, conceptually, what we want to do here is gather all of our terms that have x on them on one side, and anything that doesn't have x in it on the other side. Okay? So there's no point in adding that to both sides. We don't accomplish anything. We're trying to gather the x terms. So let's subtract this one from both sides. Okay, so that gives us x natural log of 9 minus x natural log of 27 equals minus 2 natural log of 27. Okay? Now, just like an algebra problem, combine those. How do you combine those? Factor out an x. So you have x natural log of 9 minus natural log of 27 equals minus 2 natural log of 27. Well, we've just solved for x because I can divide that by that coefficient. Remember, that's just a number. It's the hardest thing to remember about some of these functions is they're just numbers. So treat them just like they were a 2 or a 3, and you get x equals that. Now, question is how is that the same as 6? Well, it is. Can do a couple of things here. We could plug that into our calculator and prove that it's 6. Okay? But let's not take that much time because we're a little short of time here. So that's the two ways of doing that problem. Now, the second way is the far superior way if these don't happen to be numbers that have perfect common exponential bases. In other words, because they had 3 as a common exponential base, I was able to solve it in just 3 steps without using logs. But make that number an 8 or make that number 26 instead of 27, and the only way to solve it is this way here. Taking the natural log of both sides, putting the exponent down in front, doing the algebra. Okay? What else? In other words, of all the ones on this page, that was the easiest one, but notice 34 is just as easy. Do 34 for me. The quick way.
Natural log of both sides.
No? What's the common exponential base between 2 and 16?
2.
So I can write 16 as 2 to the 4th. Now what?
Well, I can't. So it's x plus 5 equals 4.
Which means x equals minus 1. Very quick way to do it if you can do it that way. Now, let's do it the other way, in case you don't realize that 16 and 2 have a common exponential base. So we're going to take the natural log of both sides. So now we have x plus 5 equals the natural log of 16 divided by the natural log of 2, which means x equals the natural log of 16 divided by the natural log of 2 minus 5. And once again, this number is minus 1. This part right here will turn into 4. And 4 minus 5 is minus 1. But you can see that the first way is the superior method if you can do it. In other words, if you have numbers that have a common exponential base. That's the better way to do it. It's quicker, it's faster, and you end up with an answer more quickly. I mean, you'd have to analyze that for quite a while to know that that's the same as minus 1. In fact, it's hard for me to even see that it is. But it is. It is. I'd have to put it into a calculator to know, because I don't know what the natural log of 16 is or the natural log of 2. So only a calculator would tell me that was minus 1. Let's do 36, because with 36 you really don't have any choices. We have no numbers that have common exponential bases. What's the first step?
Subtract 4 from both sides.
Now, do we have any numbers that have common exponential bases?
No.
Good. It was a trick question. You're right, we don't. So we can't use the common exponential base format to solve it. We have to do the natural log. So we could do log base 6. I have no problem with that, if you prefer. Seems like you probably do prefer that because it's quicker if you have an inspire. So what's the left become?
X.
And we have the answer is log base 6 of 3. I'm assuming that that's an acceptable answer if you're taking a test?
If it's a non-calculator, yeah. But if it's a calculator test, we have to...
You have to convert it to a decimal? Okay. But as long as you have that inspire, you can convert that to a decimal pretty easily. You don't have to know the change of base. In other words, change of base makes that log of 3 divided by log of 6. And these can be any logs you want. Common, natural, log base 171 if you like.
Okay.
Okay?
I think I actually get it now.
Okay. Let's go to the other page. Whoa. Sequence.
It's just number 2.
Which one, number 2?
Yeah, it's just either of the number 2s.
Either A or B?
Yeah.
Okay. What kind of sequences are these? Arithmetic or geometric?
Geometric.
Okay, good. What's the general format of a geometric sequence for the explicit A sub n?
I don't remember.
It's A sub 1, both algebraic and geometric start out a sub 1, but in this case it's times r to the n minus 1. Okay? Let's see if that works. What, first of all, is the common ratio in this geometric series?
Multiplied by 7.
Okay. First term is 5.
5.
So let's check the third term. Let's figure out, to make sure that we have the right formula here, we can see that the third term is 245. Let's make sure that it comes out to be that. What's n minus 1?
2.
5 times 49 is 245. So we have the correct explicit formula. Now, this is the general. This is not the specific explicit formula for this sequence. That would be a sub n equals 5 times 7 to the n minus 1 power. There is the specific explicit formula for that sequence.
Right.
Then find a sub 13. What's a sub 13 equal to?
So it would be 5 times 7 multiplied by 12.
Multiplied
To 12.
to the 12th power. Big difference.
12 5.
Big difference. Okay? So, whatever that number is, that's the 13th term. Now, the recursive formula. The recursive formula is the formula that tells you a sub n is equal to its previous term, always, times something. In other words, recursive means I'm going to define the nth term as a function of its previous term. Well, what would have to follow here? It would be r. Right? That's how you get the nth term. The second term of this sequence is, in other words, a sub 2 is going to be a sub 1 times 7. A sub 1 is 5 times 7, 35. So it works. Okay, so the recursive definition, that's the general formula. In our case, we know what r is. It's 7, and there you have it. Any term in the sequence is equal to its previous term times 7. In other words, the fourth term is equal to the third term times 7.
All right.
And with geometric sequences, it's always this easy. The recursive formula is always the previous term times the common ratio. What's the common ratio in B?
Multiplied by negative 5.
Okay, good. First term is 2. So the specific sequence is 2 times negative 5 to the n minus 1. There would be the explicit. The recursive would be, always start out the recursive as that, a sub n minus 1 times r, which is minus 5.
All right.
Okay. All right, Mitch, next Monday?
Yeah.
Talk to you then.
All right.
All right, bye-bye.
Bye.